Okay, so welcome to the last class meeting. So today's plan, 7.1 integration by parts. Again, kind of bridging that gap between Calc 1 and Calc 2. This coming Monday, we normally would have a class meeting, but we've pretty much exhausted all of the Calc 1 material. Um, and we're already bridging the gap between Calc 1 and Calc 2. And these topics, volumes and integration by parts, are as far as I like to go into Calc 2. uh, they kind of start into the Calc 2 material when we're in Calc 1. So Monday, we're going to take a reading day. Um, so the sample final exam is posted. So use Monday to review the sample final exam, to prep for the final exam, to finish up any, homework, anything like that. So that's what I would recommend doing on Monday. Or of course, if you want to allocate your time a little differently, you could, do that review earlier and then take Monday as a prep day for something else. So that's kind of a flex day for you. Of course, if you have any questions or you want to meet about anything um, regarding the final exam, the sample final, anything like that, shoot me an email. I'm more than happy to to meet over Zoom next week. So um, yeah, if there's something you want to meet about, let me know and we can work that out. Um, Otherwise, we'll take that as kind of flexible time. And then as I mentioned before, final exam week proper goes from Tuesday through Friday, but the exam will be open a bit early. So this coming Friday, a couple days from now, it'll be open at 9 a.m. and run through Friday the 13th at midnight. Um, it is comprehensive, chapters 2 through 5 and 6-1. And there will be a 6-point bonus problem from the material from today, section 7.1 on integration by parts. I don't think there's much else that I have to say about that. It'll be similar to the midterm exam using Examity, and it will be on WebAssign. I feel like there was one more thing I wanted to say about the final, but it just escaped me. Oh yeah, I would strongly recommend against waiting until the last day to take the final exam. I would recommend planning to take it no later than Wednesday of finals week, so Wednesday the 11th. And then if anything does go wrong, if there's a tech issue, anything like that, that gives you some buffer to reach out to me to get the tech side of things sorted out, maybe to come up with an alternative arrangement. So I would plan on taking it Wednesday at the latest, preferably even earlier than that. Okay, so any questions on anything from the material so far, anything on the administrative side of things before we get started? All right, so let's jump into integration by parts then. So I mentioned before that the integration by parts integration technique and substitution rule integration technique, these two techniques are kind of the analogous techniques to the differentiation techniques. Substitution is analogous to the chain rule and integration by parts analogous to the product rule. So let's see how that works out. Well, our product rule from derivatives says that the derivative of a product is, essentially what we do is we write the product twice, add it together, we differentiate one function in one of the terms and the other function in the other term. So the derivative of f times g is fg prime plus gf prime. We can integrate both sides to get f times g equals the integral of fg prime dx plus the integral of gf prime dx. So just taking the integral of the sum as the sum of the integrals. And then to make things look a little bit nicer, we can let u equals f of x and v equals g of x. And therefore du is f prime of x dx and dv g prime of x dx. And so what I see here after making that substitution is that I have uv equals integral of u dv f g prime of x dx plus integral of v du. So g of x f prime of x dx. So this is really just taking our chain rule, rewriting it in integral form, and making some substitutions. And then what I can do is I can solve for, say, integral u dv, and this gives me a way to take one integral and rearrange it into a different integral, right? Similar to substitution rule, we had one integral, say in x, and we substituted u equals some function of x, and we rewrote it in a different integral in terms of u. We have a similar thing here. Something that we might notice, let me copy this down here and so I can mark it up. Something that we might notice is over here, u does not have a derivative, and in a sense, v has a derivative. We're taking dv. In the integral over here, v does not have a derivative, and u does. In a sense, I'm kind of moving the derivative, right? Going from this integral to this integral, I basically just take the derivative off of g and put it onto f. Or I take the derivative off of v and move it over to u. So this is the idea of integration by parts. It allows me to take one integral, rewrite it as a different integral. Of course, not forgetting about these other details, but the end goal is to get this other integral that hopefully is more manageable than the first one. And to hopefully get a simpler integral when I move the derivative. So practically speaking, what I'm looking for as a good candidate for integration by parts is an integrand where if I differentiate one of the factors, it gets simpler. And if I integrate the other factor, the remaining bit of the integrand, at the very least, it doesn't get any more complicated. And this looks like a pretty good candidate, right? I know that if I differentiate, say, x to the first power, it just differentiates to 1. That's pretty simple. And if I integrate e to the negative 2x, that's going to integrate to something like e to the negative 2x, something along those lines. That's not going to get really any more complicated. Okay, now a side note, I mean, we're in section 7.1, so pretty obviously we're going to be using integration by parts for all these problems. But if I was just looking at this integral, not in the context of knowing which section I'm in, I would always start with the simple stuff first. I would start by asking myself, well, one, do I just know what the integral is? Does this integrand look like a function that I know is the derivative of another function? For instance, if this integrand was just e to the negative 2x dx, I just know the answer to it. It doesn't look like that. I'm not really familiar with a function whose derivative looks like x e to the negative 2x. Maybe if it was like x e to the, x squared or something like that, I might, guess that that's something like the derivative of e to the x squared, but I don't have that here. I look for algebraic simplifications, nothing really algebraically I can do to simplify this. I might look for a substitution. I'm not going to find anything really in the realm of substitutions that's going to help me here. So I'm at integration by parts now. So for all of these problems, kind of implicitly, if you were just approaching the problem, it's best to kind of start with the simple stuff and work your way up. Obviously, knowing that we're in section 7.1, these are all going to be problems that will fall pretty easily to integration by parts. Okay, so I've worked my way up to integration by parts, and I've identified that this integral does seem to be a good candidate for integration by parts because remember what integration by parts does is it moves a derivative. Can I find a factor in the integrand that gets simpler when I differentiate it and where the remaining factor doesn't get more complicated as I integrate it? And that does seem to work here. I want to differentiate the x. I see that u turns into du. U is the thing that's picking up a derivative. So I want to choose for u the thing that gets simpler when I differentiate it, in this case, x. And then what's left over is going to be dv. So I chose this to be u, and this bit is going to be dv. And just like I've talked about for several I guess class meetings now, dealing with integrals, the kind of bookkeeping, as I like to call it, is quite important. So we want to make sure that we've used everything in the integral and nothing that's not in the integral. I didn't throw in an extra, factor anywhere. I didn't miss any factors. And I do see the x, e to the negative 2x dx. That is exactly u times dv. I know for my integral on the right, I'm going to need to know what is v and what is du. So let me calculate those. Du is u prime of x dx, or just dx. And then v, I want to integrate e to the negative 2x dx. That's going to look like e to the negative 2x. If I were to differentiate to get back to dv, this would give me e to the negative 2x times a negative 2. I need a negative 1/2 to make that work out. And again, I'm only looking for an antiderivative here. I don't need the most general. I don't need to put in a plus c or anything like that. And let me clean up my formula up here. So I have integral of u dv by integration by parts equals uv. So that's the product of these two. X times negative 1/2 e to the negative 2x minus the integral of v du. And I'm writing everything out really carefully here. When you get a little more used to the formula, you can maybe skip a couple of steps here and there, or simplify things as you go along. But v du is negative 1/2 e to the negative 2x times dx. That whole integral has a minus in front of it from the formula. So there's a minus there from the formula and an additional negative 1/2 from what v is. Or I see this as negative x over 2 e to the negative 2x minus a negative is a plus 1/2 integral e to the negative 2x dx. Okay. And now I'm left with an integral that I'm able to do. It's, I don't want to say trivial. It's not a trivial integral, but it's an integral that I can do pretty readily. That I just recognize that e to the negative 2x is more or less the derivative of e to the negative 2x. Integrating this gives me e to the negative 2x. If I differentiate, I would get e to the negative 2x times a negative 2. I need a negative 1/2 to counteract that. And now that I don't have any integrals left over, I better throw in a plus c at the end of all of this. And what do I end up with? I guess I end up with a negative 1/2 e to the negative 2x times, I get an x from the first term and a plus 1/2 from the second term, and then a plus c at the end. Be careful that that plus c is all the way at the end. It's not like in the middle of the brackets or anything. It's not multiplying that e to the 2x stuff. And here at the end, I do see that I got something that I probably wouldn't have guessed as the function whose derivative looks like x e to the negative 2x. So, this was a good candidate for integration by parts. Any questions so far? Let me bring our formula down. As an aside, there are some mnemonics that people use to memorize the integration by parts formula. You can just rederive it from the product rule. It's not that cumbersome, doesn't take that long. But there are some mnemonics. I know that the one that I was told in college is probably not good to share now that I'm in this position, but you can look up mnemonics yourself, and quite often the the sketchier the mnemonic, the easier it is to remember. So um, I won't enlighten you with what I was told in um, Calc 1 or Calc 2 to remember this, but you can look them up online, I'm sure. Okay, next up, this example, integral of the natural log of 3x dx. One thing we got to be a little careful about, um, just thinking of heading into the final exam, when you're fairly new to integrating, you can kind of mistakenly like go the wrong direction. You can think that this is going to look like 1 over x. But remember, that's differentiating. So we're integrating, we're looking for the function whose derivative looks like log of 3x. Right? So the derivative of log of 3x looks like 1 over x, but whose derivative is log of 3x? That's the question we're trying to answer here. So I don't just recognize this as I don't recognize that log of 3x is the derivative of a known function. Nothing really much that I can do to simplify things here, although maybe that's, there might be a little bit of simplification I can do here, but it's not going to really help too much. The log of the product's the sum of the logs, so I could make this log 3 plus log x, but I still have to integrate log x. So I'm still kind of, morally speaking, in the same level of difficulty. So even though I could do maybe some algebraic simplification, doesn't really help. Substitution is not likely to be helpful. Again, if I knew how to integrate log u, maybe that would help, but integrating log u du is essentially just as challenging. And then I look at integration by parts, and my kind of immediate reaction is, well, I can't do integration by parts here because I need two things multiplied together, like this x times the exponential bit here, right? And I kind of only have one thing here, log of 3x in the integrand. But actually I can make a little bit of headway here. I do notice that if I could differentiate log of 3x, I'd get a 1 over x. And that would be a lot easier to deal with. So integrating 1 over x is just like integrating x to the minus 1. It's just, it's gonna work a lot better than this log floating around. I would love it if u were log of 3x. But then what is dv? Well, actually, I see that I've used the log of 3x bit, but I still haven't used the dx bit. dv can just be dx, or if you really wanted to be pedantic, you can make it say 1 dx, right? Log 3x is just log 3x times 1. But basically, dv is just dx. Right, going all the way back up here, this would just be where like our um, where our g of x is just 1. Or sorry, where our g prime of x, that's the one I'm looking for, is just 1. Okay, so u equals log of 3x. Du then is going to be, we could do like 1 over 3x times the derivative of 3x is 3, or we see it's just 1 over x. Or we could think of log of 3x as log 3 plus log x. The log 3 differentiates to 0, and we have 1 over x. And v equals x. And by integration by parts, this is uv minus, again, the minus comes from the formula, so don't forget the minus integral of v, and then, oops, log of 3x differentiates to 1 over x dx. Du is 1 over x dx. So 1 over x dx. Or this gives me x log of 3x. Well, x times 1 over x is just 1. Integral of dx is just x. And since I've gotten rid of all my integrals now and I want the most general antiderivative, which is what that indefinite integral signifies. I'll throw a plus c on at the end. So again, this isn't a function that I would have immediately thought of, whose derivative would be log of 3x, but this is what we get from integration by parts. Any questions so far? Let me bump this down to another line. With these definite integrals, sometimes especially a definite integral with the fraction, sometimes the bounds are hard to read. Let me do actually the same up here as well. There we go. Get the formatting a little better in case you're on a small screen. Something that we note is that, of course, integration by parts can be used for a definite integral as well. Right? We can just evaluate the left and right side up here from a to b, and we get that the integral from a to b of u dv equals uv evaluated from a to b minus integral a to b of v du. So if I look at this example, the fact that it's a definite integral versus an indefinite integral doesn't really change my technique. The only place that it might change my technique is if I recognized the integrand as some kind of special geometric structure, like a circle or something like that, and maybe then the bounds of integration turn out to be, say, like a quarter circle or something that might make it easier to do that integral. But I don't see anything like that here. So the fact that it's a definite integral really doesn't change my integration technique. I'm still going to take the same technique that I would before. And again, we're going to use integration by parts here. We would go through and think about if is there anything else that we could do to is there a simpler technique we could use here to get this integral? And the answer is no. So we're looking for, in this integrand, something that I can differentiate and becomes easier to deal with. And hopefully then the rest of the integrand I can integrate and doesn't become much more difficult. And actually I see that again, this log of y is the thing I really want to differentiate. So I want to pick u equals log y, so the du is 1 over y dy. And then if I've used log y on the top here, for u, everything else is going to be 1 over root y dy. So all of the rest of this becomes my dv. I've used everything in the integral and nothing that's not in it. Du now is 1 over y dy. And v, well, I know that the derivative of square root of y, the derivative with respect to y of the square root of y is like 1 over 2 root y. So if I differentiate root y, I get 1 over 2 root y. I need a 2 here, so I get 2 over 2 root y, or just 1 over root y. So v is going to be 2 square root of y. Something really important to note about the integration by parts formula, in substitution, we went from integral, what was it, f of g of x, g prime of x dx, to integral f of u du. Our variable of integration changed, which means that our bounds had to change as well. If we look back at these examples, variable of integration was x, variable of integration is still x, right? Variable of integration is x, variable of integration is still x. We do have some u's and v's floating around here, but they're really just kind of like placeholders to make sure that we slot all of the stuff, all of the x stuff in at the right place. So we're not actually changing variables here. We're not actually making a substitution here. My bounds just stay the same. It, at a first glance, we look at this and we say, wait, I think I've changed from the variable integration being v to being u. Shouldn't I need to change my bounds to respect that? But no, the variable of integration is still the original variable of integration. These u and v bits here, they're placeholders to make sure I slot in the correct functions in the correct places. Or, I mean, I suppose you could really say we're kind of making a substitution and then immediately undoing it. You know, you could think of it that way too. But either way, the point is I don't have to change my bounds. So uv is 2 root y log y evaluated from y equals 4 to y equals 9 minus the integral from 4 to 9 of v du. 2 root y over y dy. Everything here is still y's, right? It's still the same variable as the original variable of integration. It's not like we've changed variables to u or something like that. So all of these bounds stay the same, right? Different scenario from the substitution rule, which also happened to use the letter u. But here we were actually changing variables to a different variable u, and that's why we had to change the bounds there. So keep that straight between the two techniques. Substitution rule, we are changing variables. We do have to change our bounds of integration if we're going to do everything in one line. Integration by parts, we're essentially not changing variables. We're maintaining our same variable of integration, and u and v are just kind of helping us slot the right functions in at the right places. Okay, so I have this first bit, which is 2 times square root of 9, or 2 times 3 is 6, log 9, minus 2 square root of 4, 2 times 2 is 4, log 4. And then minus, well, 2 root y over y, that's just 2 over root y, right? Y is kind of like square root of y times square root of y. I can divide out my square roots of y. So that's 2 over root y, or that is, well, I guess we can leave it like that. 1 over square root of y integrates to something like square root of y, right? Just like up here, we have the same pattern. But that 1 over square root of y, if I differentiate square root of y, I get 1 over 2 root square root, 1 over 2 square root of y. I need another factor of 2 to cancel that extra factor out. So I have one factor of 2 coming from here, another factor of 2 coming from integrating 1 over root y. That was the same integral that I did up here. So I have 4 root y evaluated from 4 to 9. And I have 4 times square root of 9 is 3, minus 4 times square root of 4 is 2. Making sure that this minus applies to this whole thing here, that whole result of that integral. Okay, I can simplify this just a little bit, I suppose. Log 9, well, that's log of 3 squared. The 2 can come down. I guess that's 12 log 3 minus 8 log 2. And it didn't make it look a whole lot nicer, but at least my arguments of the logs are a little simpler. And then I have 12 minus 8 is 4, so minus 4. That's my answer. Remember, definite integral, we're getting a number out. This is the actual area between y equals 4 and y equals 9 under this curve, and that's my answer. So no plus c's or anything at the end here. We're just getting a number out as the answer. Questions so far? Okay, so strategically speaking, if I am looking to use integration by parts on an integral, how should I choose u And, as a typical rule of thumb, it's pretty good to choose u as the first element in the following list. Logarithms, because remember, u is the thing we're differentiating, and logs get a lot easier when we differentiate them. We go from a transcendental function, say log x, to just a power function, 1 over x. The power function is a lot easier to deal with. An inverse trig function, something like, arc tan x, is really annoying to deal with. But if I differentiate it, it becomes 1 over 1 plus x squared. It's like almost a power function. An algebraic function, so essentially a power function or a polynomial, something like that. When I differentiate a quadratic, it becomes linear. Differentiate a linear, it becomes constant, right? So that gets easier when I differentiate it. And a trig function, I mean, sine or cosine, when I differentiate it, it just goes to the other one. So it doesn't get a whole lot easier. It doesn't get much worse, but it really doesn't get much easier. But, I don't know how far this is going to get me. And same with an exponential function. I differentiate an exponential, I get an exponential back. It probably doesn't get worse, at least not for, lots of exponentials. But maybe it's not going to get a whole lot nicer. So let's look at this example. Here, let me again bump this down. Oh, all right. This one's just not cooperating very well. I was hoping to make it a little bigger on your screen, but no such luck. Oh, maybe this is the issue. All right. There we go. I don't know how much that helped, but I figure if you're on a small screen and we have exponents or fractions or whatever, sometimes it gets a little hard to read. Okay, so I want to do integral of e to the negative theta, cos of 2 theta d theta. These types of functions, negative exponentials against trig functions, come up in solutions to differential equations. We have basically a trig function with an amplitude that is an exponential decay. So I have like an exponential decaying amplitude. And I guess at theta equals 0, I'm at 1. So I start up here. And my trig function just bounces back and forth between these two curves that are defining its amplitude. These come up in solutions to differential equations that have oscillatory solutions that decay over time. So for instance, like if you had a mass spring system, here's a mass that's attached to some spring, and it's sitting on the ground, and you stretch the mass and it goes back and forth from equilibrium, except it encounters some air resistance, some rolling friction with the wheel down here, and so on. So over time, it decays. Over time, that energy of stretching the spring and letting it go, the energy input into the system gets dissipated in the environment as noise or heat or something like that. So we get an oscillatory solution from the kind of inertial term and from the Hooke's law, the Hooke's law term, the term of proportionality, that if you stretch the thing twice as far, the spring pulls twice as hard. And that's what leads to the oscillatory part of the solution. But then we have a first derivative part of the solution that says when the thing is moving, when it has speed, when it's moving, it's encountering things like air resistance and doing things like making sound vibrations and so on. And that's sapping energy out of the system. So anytime a system is moving, it's having energy sapped out of it. It's encountering damping, and that's what makes the oscillations go down, right? Same way if you pick up a kid on a swing and let them go, they're going to start at a certain height. When they swing and come back, they're not going to come back quite to the same height. There's a little bit of friction with where the swing attaches to the support, and it makes a little bit of noise and so on. And even ignoring any inputs the kid might have, swinging their feet or whatever, they're still not going to come quite back up as far as they started. So That's where these types of functions, where you see these types of functions, negative exponentials against trig functions. Okay, so how do I do this integral though? This integral is not a very easy integral to do. It's not going to fall to any of our easier earlier techniques. You can check and make sure that it doesn't, but it won't. I do see that I have the product of two functions here. So when I run into integration by parts, working my way up my techniques, I say, okay, maybe integration by parts will work here. What do I want to differentiate? What do I want to integrate? It kind of doesn't much matter, right? I probably would rather differentiate the trig function because integrating an exponential kind of works the same over and over. But differentiating a trig function, sometimes we pop out a negative, sometimes we don't. And also I see that the interior of the trig function is a little more complicated. But I think it's basically a toss-up here. Let me choose u equals cos of 2 theta, and dv equals e to the negative theta d theta. V then is going to be negative e to the negative theta. Du, the thing that I'm usually hoping is going to get quite a bit simpler, well, cosine differentiates to negative sine, and a 2 pops out, so I have negative 2 sine 2 theta. I need a d theta there as well. These are all thetas, not zeros, but there we go. Unfortunately, my du isn't all that much simpler. Let's follow our noses and see what we get, though. Just a reminder that this is our formula. Oh, this one. So I need uv, negative e to the negative theta, cos of 2 theta, minus, this minus is coming from the formula, integral of v, which has another minus on it, du, which has another minus on it, so let's see, did I get everything right? Minus integral of v, negative e to negative theta, du is a negative 2 sine 2 theta d theta. Looks good. Let's simplify this a little bit. I have a minus, another, and another, so that overall that's a single minus sign. I'm going to put that 2 out front for just a minute. And this is what I end up with. I actually end up with an integral that looks kind of similar to my first integral, right? So what can I do here? I have an integral that looks similar to my first integral. I might ask myself, what if I did this again? Could I apply integration by parts to this integral? This sine 2 theta would differentiate to something like a cos 2 theta. This e to the negative theta would integrate to something like an e to the negative theta. And then I get my same integral back. In other words, I might end up with something like I equals f of theta plus ki. I might be able to solve for my integral, right? Subtract ki over. I have 1 minus k times I equals f of theta, and then divide by 1 minus k. So that's my strategy here. I don't think this would be an easy strategy to come up with if you hadn't seen it. So kudos to whoever was the first one to to think this up. Maybe they just followed their nose and kind of recognized this pattern and saw that they could keep going. But that's going to be our strategy. So I want to apply integration by parts to this integral. I have a little bit of a challenge here. When I end up with the result of this, I'm going to have a uv minus integral v du, but that whole thing needs to be multiplied by this -2. That's just kind of annoying, right? I'm probably going to forget about that -2, or I might distribute it wrong or something like that. If I'm going to apply integration by parts more than once, overwhelmingly what I'll do is move that -2 inside. So I'll make it a plus integral of, say, -2 e to the negative theta sine 2 theta d theta. Let me make sure I didn't miss anything here. Basically, I just pulled this minus out to make that a plus. I've nested everything of importance inside of my integral now. I'm basically embedding it in the u's and the v's, and that's going to put everything in the right place for me. So I don't make any, simple algebra flubs. It would be a shame to do all the calc right and make a goofy distributive property flub at the end, forget to distribute a negative or something, and have something wrong. Okay, so again, if I choose, u equals this and dv equals this, I'm undoing what I did before, right? Because let me scroll up to the f and g bit here. What I had done before was take a derivative from, say, g and put it onto f. But then if I reverse my u and v, then I just take the derivative from f and put it back on the g. I just undo everything, right? So I just end up with I equals 0 plus I. That's not very helpful. So I need to keep going the same direction. So I chose u to be the trig function first. I need to choose u to be the trig function again. As an exercise, you can try doing your u and v backwards here and see that you get, you're going to get what, a plus e to the negative theta cos of 2 theta, and then plus the integral that we started with, and you just get I equals 0 plus I, and that's not very helpful. I mean, it's not wrong, but it just doesn't help us. But I'm going to choose u to be the trig function again. I'm going to choose dv to be what's left, -2 e to the negative theta d theta. Du then is cos of 2 theta. Sine differentiates the positive cos, and then we pop out a factor of 2 with the chain rule, d theta. And then v, my e to the negative theta, integrates to e to the negative theta. The negative sign coming down from that gets rid of the negative sign in front of the 2, just leaving me with 2 e to the negative theta. Okay, so this bit I didn't touch, so it just comes down. And then plus, again, the result of my integration by parts, uv. So 2 sine 2 theta e to the negative theta. I don't know why I wrote them in different orders, no particular reason there, but minus integral of v du. And I see that I have a factor of 4 that can come out, so that's 4, and those come out. And I note that I end up with integral e to the negative theta cos 2 theta d theta. If I name this integral I, that's an I of theta, but we'll just call it I see that I have, get that back on the screen, I see that I have I equals, what is it? E to the negative theta times 2 sine 2 theta minus cos 2 theta. That looks right. And then minus 4. And this again is just the integral I. Or I end up with 5i. Note that 5i is just 1 squared plus 2 squared. That actually comes from the 1 in the power up here and the 2 inside of the trig function there. So this kind of has the feel of kind of combining two trig functions together, like with two amplitudes or something. It has that like a squared plus b squared kind of feel to that. But we end up with 1 plus 4 is 5i equals all of this stuff. Or in other words, my original integral, equals 1/5 e to the negative theta 2 sine 2 theta minus cos 2 theta. Any questions on that? So another example of a kind of an interesting use of integration by parts that we might not have thought of right away, because it seems like both of my factors don't get easier as I differentiate them, but at least they don't get harder. And I see that if I apply integration by parts twice, kind of continuing to go in the same direction, so to speak, you could have done this by choosing u as the exponential and dv as the trig, and then you would just have to use the same, choose u as the exponential and dv as the trig function again the second time. You'd get the same answer. But by doing that, I ended up with I equals f of theta minus 4i, and then I could solve for I. And like I said, if you flip-flop them, you would have gotten I equals 0 plus I. And I mean, there's nothing wrong with that, but it's just not helpful. You just get I equals I. Any questions so far? Okay, we've got one more problem to work through, and this is probably on the moderately challenging to difficult side of integration by parts. So if I look at this example, I want to integrate square root of x times e to the square root of x dx. Now I look at this and I notice that it looks a little bit like x e to the x, right? Or like u e to the u or something like that. It looks a little bit like the very first one that we did, kind of in some sense. So I have a gut feeling that maybe integration by parts is going to work here. I mean, I can differentiate square root of x okay. That's not the nicest thing to differentiate. But how do I integrate e to the root x? Like, that's not going to be very nice. So I look at this and I see this pattern that it looks like something that I've used integration by parts on before successfully. But it doesn't quite fit that pattern nicely enough to use it right out of the gate. Can I maybe massage this into a form that makes it more amenable to an integration by parts? Particularly so that I end up with an exponential that I can integrate. I can't integrate e to the root x dx. Can I rewrite this in terms of something I can integrate more easily? Well, I might think to myself, hey, it would be really nice if this was just, say, e to the u. Let's shoot for that. If I pick u equals root x, so here we're, by the way, we're doing, actually, let me just use a different variable altogether. For substitution, maybe we'll choose s. s equals root x, because we're going to have other u's and v's later on, and I don't want to get them confused. So s equals root x. I'd like to substitute into this new variable x, or new variable s. That would make an e to the s here, and I can definitely integrate an e to the s ds, so that wouldn't be bad. Does the rest of it work out? So ds is 1 over 2 root x dx. I don't see a 1 over 2 root x in my integral, but I could, let me come off to the side here, choose to rewrite this integral as 2 root x over 2 root x. That's just multiplying by 1 times the stuff that I had before. And I'm being pretty careful and deliberate here because there's just a lot going on. So I'm making sure that, okay, I've multiplied by 1. So I haven't done anything, sketchy to this point. And the root x, e to the root x dx, that's everything else that was in there. Now I can combine these bits together. 2 root x is 2x times 1 over 2 root x e to the root x dx. Okay, I have my 1 over 2 root x dx. I have my ds. I have an e to the s now. And it might seem like, like I'm playing like whack-a-mole. I solved one problem with x's, but I got another problem with x's. What do I do with this guy? Well, nicely enough, s is square root of x, so s squared is just x. Okay. So using this substitution, integral of root x e to the root x dx, with all of this work over here, turns into 2s squared, or integral of 2s squared e to the s ds. Okay. Now that looks a lot nicer because a lot nicer to work with because I can integrate this, and when I differentiate this, it does get simpler. I mean, a quadratic goes to a linear, it doesn't get super simple right away, but it gets easier to deal with anyway. So let me choose u equals 2s squared, dv equals e to the s ds. I've used everything in my integral, nothing that's not in it. V then is e to the s, du is 4s ds. Okay. This integral becomes, by integration by parts, uv 2s squared e to the s minus, this minus is from the formula, integral v du. 4s e to the s ds. I end up with an integral that's simpler than the one I started with, but not quite easy enough for me to just know what the result is. But I do recognize that this was the same type of integral that I had up here. I think if I hit it with integration by parts one more time, if I hit that that algebraic term, that 4s, with one more derivative, then I'm just going to end up with an integral of e to the s, and I'll be able to write down the solution then. I'm going to do the same thing that I had done before, is move this minus inside of the integral as a plus, say negative 4s e to the s ds. That way I don't have to worry about distributing that minus to both of the terms and everything. I already have a bunch of minuses floating around, a lot of complexity already. Might as well not add any additional complexity. So this is going to be, I'm not doing anything to this first term. Let me get myself a little extra room here. This first term just comes down. And now for my integral, I'm going to do integration by parts again. U, the thing I'm differentiating, is going to be negative 4s. dv is everything that's left over, e to the s ds. du is negative 4 ds. And v is just e to the s. And now again, since I have a plus here, I don't need to worry about distributing anything like that. Just a plus uv minus the integral of v du. And basically my integration by parts formula, tracking through all of the u's and v's and so on, that essentially did that distributive property for me, is really what it did. So simplifying a little bit, I have 2s squared e to the s minus 4s e to the s. If I pull the minus 4 out, I get a plus 4 integral of e to the s ds, which is, of course, just e to the s, and plus c. Or maybe I would simplify this as 2e to the s squared minus 2s plus 2 plus c. I think that is about the best we can do here. Any questions on this example? So this would be on the more challenging end of integration by parts integrals, because we needed to actually do a full integration technique, substitution, to get this integral into a form where we can do another integration technique, integration by parts. But we probably did, recognize this, especially having just done that other problem. We probably did kind of recognize this form as a form that's kind of similar to this, and that might have given us a clue as to where we wanted to go. Right? I want to treat this the same way that I treated the other one, but the other one worked nicely because the exponential was easy to integrate. This exponential was not easy to integrate. Can I move the complexity out of the exponential, making it easy to integrate? Essentially move that complexity to the other bits, and hopefully end up with something that is reasonable to work with and to differentiate and so on. And that does work out here. There might be other examples where you want to move the complexity out of the exponential and it's infeasible to do. All of the junk that you get from the ds and all of that just makes too much of a mess, and you end up with an integral here that you still can't deal with, and you might have to use a different technique to approach something like that. But in this case, it worked out okay. So I think another thing with integration that makes it a little difficult is, we can layer these techniques together. With derivatives, it's kind of like you just follow a process, right? You do this thing, then this thing, then this thing, and you get your answer. With integrals, it's like you're almost like solving a puzzle. So sometimes this this technique works right away, or that technique is easy to see that it applies, but other times I might have to do some algebraic simplification and then see that an integration technique applies easily, or layer two integration techniques together. And how do you get used to seeing that? How do you get to the point where you look at this and you say, oh, that looks like something I might want to do integration by parts on. This would be the bit I want to integrate, but it's annoying to integrate. How can I get over that hurdle? How do you get to that first step, though? Well, it's really with trial and error and practice and pattern recognition. One of my professors in grad school always liked to say he was the Georgia State chess champion when he was younger. And he always used to say, chess is a game of pattern recognition, math is a game of pattern recognition. I don't care how much you read about, forks or pins or skewers or whatever it may be in a book, you're not going to be good at them until you've played 100 games or 200 games and have actually found that, that technique or that tactic a bunch of times in real games, and then you start getting good at it. Or there's this saying in Go, the abstract strategy game, with the little black and white pebbles on the board. Um, so somebody said in Go something like, the best way to get out of the beginner stage at stages of Go is to lose 100 games as fast as you can, right? If you're super worried about winning games, you're going to like study and study and study and try to like apply all of the tactics. But the point is, you just need to lose a bunch of games. In other words, you just need to jump in and play a bunch. And because you're a beginner, you're going to kind of stink and you're going to lose a whole bunch of games. But that's building up that pattern recognition where you see, oh, I've done this same thing like 5 different times and it hasn't worked any of those times. That might not be a good thing to do. Or I happened to do this other thing 5 times and it worked 4 of the 5 times. That might be a good thing to do. And you start to realize what are the good things and the bad things to do and what kind of things work or don't work. And uh, then maybe you get better quickly. So same thing with these integrals, right? Going through a lot of practice with just seeing a lot of integrals where you use substitution, where you use integration by parts, or when we get into Calc 2 proper, if you're in Calc 2 next semester, the other integration techniques we'll see, just drilling, those techniques really gets you used to them and really makes you aware of what patterns to look out for. All right, any questions on integration by parts? Okay, so that really wraps up our material for the course. Are there any questions at all about Calc 1? Questions about anything that we covered, looking forward to Calc 2, anything like that? The final exam, the administrative side of things. Any questions before we break for today? Okay, I will stop the recording then.